In this video, we're going to talk about the meaning and use of quantum numbers in describing electrons in the hydrogen atom. You remember from previous discussions in class that the solutions to the Schrödinger equation provide information about the electron, psi, the wave description of the electron, and the quantized energy for the electron in that state. Psi squared is interpreted as the probability of finding the electron in a given region of space at a distance r from the nucleus. Usually, we'll describe a region in which there is a 90%, say, probability of finding the electron, and we'll talk about that. And that 90% probability area we'll call an orbital. Associated with each psi are a set of three quantum numbers, n, l, and m sub l. These quantum numbers are essentially used by chemists as shorthand notation describing the electron, the energy, and the probable position. In other words, these quantum numbers are going to describe the orbital, which is the area where the electron is most likely to be found around the nucleus. A fourth number not directly solved from the Schrödinger equation, but later added in due to the work of Wolfgang Pauli, that fourth quantum number ms describes the spin of the electron. So here are the four quantum numbers nl, ml, and m sub s. N, as you recall, describes the principal energy level for the electron. L, which is technically called the azimuthal quantum number, which is a mouthful, so generally everyone just says the shape quantum number, and it describes the shape of the probability density where the electron will be found. In multi-electron systems, L also has an impact or a role in the description of the energy for the electron. So if you're talking about just one electron systems like the hydrogen atom, then N is energy and L is simply shape. But when we go to multi-electron systems, L also affects the energy. M sub L is the orientation. So if a particular shaped orbital can be oriented differently with respect to an XYZ space, then that ML will describe the orientation of the orbital in that space. And then, of course, as we noted, ms is the spin of the electron. Each electron is going to have a unique set of quantum numbers. And what we'll find is that those quantum numbers provide a complete description of the electron wave. And we'll be using those then as our shorthand notation, as mentioned, to quickly understand some of the properties of the electron. So let's talk about what states are available to the electron at a given principal energy level. In other words, what orbitals described by n, l, and m sub l are available to the electron at any given principal energy level. You'll recall that the principal energy quantum number n has integer values. So we'll list just 4 energy levels, starting from the bottom and working our way up in energy. I just want to note that your textbook has the opposite order. Very similar table to what I'm going to produce here, but starts with n equals 1 at the top and then works its way down. L can take on values ranging from 0 through integer changes up to n minus 1. So in other words, L at principal energy level of 1, n equals 1, can only have one value, right? Because it's going to range from 0 up to n, which is 1, minus 1, which is 0. So it ranges from 0 to 0, so just one possible value. In other words, there is only one orbital at energy level 1. and it's described by L is equal to 0. At n equals 2, L values can take on 0 up to n minus 1, which is 2 minus 1, which is 1, and therefore we have 0 and 1 as the possible values. In other words, there are two orbitals, right? Two different shapes of orbitals possible at energy level 2. And of course, when we go to n equals 3, we have L values ranging from 0 up to 3 minus 1 in integer changes. So that would be 0, 1, and 2. You can pause here and work out what are the values for L at principal energy level n equals 4. Okay, so for n equals 4, we will have L values going from 0 up to 4 minus 1, which is 3, 0, 1, 2, and 3. And so there are 4 different shaped orbitals possible at n equals to 4. And you can see that the allowed shapes increases as the energy levels increase. And those shapes will become increasingly complex. Now, chemists generally describe the shapes of orbitals with letters, for historical reasons, rather than numbers, or in addition to the numbers. For L equals 0, we describe the orbital as being the s orbital. For L equals 1, we have what is called a p orbital. For L equals 2, the d orbital. L equals 3 is the f orbital. 4 would be g, and then after that they just follow alphabetical order. The shapes of those orbitals are as indicated here. The s is spherical. The p orbital has a sort of dumbbell shape. The d orbital has this bilobal or double dumbbell shape. The dark spots in these indicate the greater probability of finding the electron, and as the color fades, I meant that to indicate the decreasing probability of finding the electron in those regions. So these are the shapes for the orbitals with L equal to 0, which is the s orbital, 1, the p orbital, and 2, the d orbital. The orbitals become more complex in shape as L increases. There's some wonderful images and even interactive orbitals that you can rotate around on a site called the Orbitron. I encourage you to go look that up. Just do a Google search or Bing search or whatever your favorite search is for Orbitron, and you should find it. And you can look at the more complex ones. For us, we will have the expectation that you will be able to draw the shapes of the s, the p, and the d orbitals, and we'll stop there. Now, let's look at the orientations that are available to these orbitals. The orientations being described by the quantum number m sub l. M sub l ranges from L to negative L and changes in 1 integer increments. So, in other words, for an L value of 0, say at the principal energy level n equals 1, L equals 0, then ML ranges from L0 to negative 0, which of course is just 0. So we have only one possible orientation then for that s orbital, and that has ML value of 0. Now that's the same no matter what energy level you're at. So at principal energy level 2, we have an s orbital described by L equals 0. That also has only one possible orientation, ML value of 0. The p orbital, described by L is equal to 1, has 3 possible orientations. And those go from 1 up to, or down to, negative 1 in 1 unit changes. So that would be 1, 0, and negative 1. At n equals 3, the s orbital, L equals 0, still has only one orientation, The p orbital at n equals 3 has 3 orientations. The d orbital, described by L equals 2, has L ranging from 2 to negative 2, changing by 1 unit increments. So that would be 2. 2 minus 1 is 1. Minus 1 again is 0. Negative 1. And then down we stop at negative 2, or negative L. And so there are 5 different orientations possible for the d orbitals. Now these orientations are independent of the energy level. So again, to reiterate, s orbitals have only one possible value of ml, 0, so just one orientation. P orbitals, whether you're talking about the orbital at level 2 or the p orbitals at level 3, have 3 possible orientations. And d orbitals always have 5 possible orientations. We'll look at the orientations for the p and the d's in a moment, but just for now, let's look at the orientations of the p orbitals described by mLs of 1, 0, and negative 1. We have 3 rotations of the p orbitals, one with that dumbbell along the x, one with the dumbbell shape along the z, and one with the dumbbell shape along the y-axis in an xyz coordinate system. And these are then the 3 orientations of the p orbitals that are possible. The d orbitals will have 5 orientations, and we'll look at the pictures of those in just a moment. But before that, I just briefly want to go over the relative energies of these orbitals, which are, as we mentioned, for one electron systems, are dictated by the principal quantum number n. If we write a little diagram with energy and an arrow showing increasing energy, then the lowest energy orbitals will be in the energy level quantum number 1. And so we'll just write a dash for that orbital, which I've shown here in blue, and write 1s under it. So in other words, this is the relative energy for the energy level 1, of which there is an s orbital. And since there's only one orientation, we just have 1 dash shown. At energy level 2, we have the 2s orbital, which has only one orientation, so 1 dash, and then we indicate that it is the energy level 2, and this is our s orbital shape, the spherical shape. Also at that energy level are 3 2p orbitals, the 3 orientations of the p orbitals that were possible. So I have a dash for each of those different orientations, and then below it we just write 2p for the energy and the shape of the orbital. And then as we go up in energy, now to the 3rd level, we have the 3s, 1 dash for its one orientation, the 3p, 3 dashes for the 3 orientations of the p, and then for the d, we have 5 orientations, so I wrote 5 dashes, and then below it indicate the energy level and the type of orbital or the shape of the orbital, which is the d orbital. Now again, keep in mind that these energy levels are for a 1 electron system, and so only n determines the energy, right? So each orbital, the s and the p, have the same energy at principal energy level 2, and the same for our energy level 3. However, when we go to multi-electron systems, these orbital energies are going to shift. So in other words, the 3s, the 3p, and the 3d will no longer be equivalent in energy in a multi-electron atom. So now let's look at the shapes of the d orbitals along with the p and the s and their orientations. We'll also look at the symbols that chemists use to indicate orbitals of different orientations on the x, y, and z coordinate system. So starting with the s orbital, remember that s orbitals are always spherical regardless of the energy level, and so that only has one orientation on the x, y, z axis. The p orbital, we mentioned, has 3 different orientations along the x, z, and y axes. Those orbitals are designated as the px for the one along the x, the pz for the orbital oriented along the z-axis, and the py for the orbital oriented along the y-axis in the coordinate system. The d orbitals have more complex, sort of a double-lobed shape or two-dumbbell shape, except for the dz squared, which you see has one lobe and then a sort of circular donut shape, they usually call it, on the xy plane. Now, those different orientations are designated as the dx squared minus y squared, indicating the d orbital that has the lobes directly on top of the x and the y-axis. Then the dxz orbital, which has the lobes oriented right between the z and the x-axes. The dyz has the lobes in the plane of the z and the y-axis, those axes, and then the dxy has the lobes in the plane of the y and the x-axes, sort of right in between the axes here. You should be familiar with the shapes and orientations for all the orbitals and be able to draw orbitals on a XYZ coordinate system. So in other words, be able to draw a dxz, a dyz, a pz, a py, and the various orbitals.